As we continue in 5.1, what we did last time is we looked at how if we take a finite number of rectangles, we can get an approximation for the area under the curve. And so as we continue that conversation, what I want us to look at is thinking about, okay, so suppose that we have the function f of x equals x squared on the interval from 0 to 4. And what you see in the left-hand column here is the lower Riemann sum, and then what you see on the right-hand side is the upper Riemann sum. And it occurs to me I might not have yet used the phrase Riemann sum. So when you see that, you're really just talking about the lower and the upper sum that we talked about before. So as we look at the lower sum, because this is an increasing function on the interval from 0 to 4, then it's going to be left endpoints, and then on the right hand side the upper sum is, because it's an increasing function, the right endpoints. And so what I want you to notice is we start off, and this was done with Maple, so they refer to the number of rectangles down below here. It's what they refer to as the partitions, equal to 8. And then up above is where you see the actual area of those rectangles. And so here's what I can see. With 8 rectangles, my lower sum is 17.5 and my upper sum is 25.5. So at this point we could say the actual area obviously falls somewhere in between these two, but we can actually visually see the error, right? I mean, we can visually see, if I look on the right hand side here, I mean, I can see this overestimate. If I look here, if I look at the rectangles on the lower sum, I can see the error here. I can see what it's missing. So we can see visually the error. Now suppose we increase, though, the number of rectangles. Now we double it and we're up to 16. So a couple of things we look at. First of all, just the visual of the error. I can see with my lower sum, the portion that's not represented that I would need has gotten smaller. And same thing over here on the right, the overestimate portion. You know, as I'm shading, it's a lot harder for me to shade this in. Like, looking at this error, it has gotten smaller. We can also see that the values of the lower and the upper sums are getting closer to each other. And so now we're somewhere between 19.375 and 23.375. And so we continue that. So next I doubled, and I'm again now doubling my partitions. I'm at 32. So 32 rectangles. Visually, it's going to be really hard for me with my pen to shade in the error, although you can still see it. I can visually look at this and see the under and the overestimate in each of these. But notice now I'm getting within 2 or so of units of the actual area. The under is 20.3, the over is about 22.3 square units. Now, as I continue doubling my number of rectangles, I'm going to 64, and then down below here I'm at 128, and now we're getting to the point that it's hard to even visually see where that error is. I can also see that I'm getting down to, about 1 in terms of being able to bound the actual area in between the lower and the upper sums here. So once I get to this many rectangles, visually it's not even gonna be useful to show the graphs anymore because I can't even really see it. But as we look at now, just omitting the graphs and looking at the outputs, if I keep doubling my number, which is just what I chose to do in Maple, I'll keep doubling my number of rectangles, and then looking at my lower and upper sums here, we can see that this actual area is now, by the end here, it looks like I can get accuracy to the nearest hundredth. So it's somewhere between 21.33138 and 21.33528. So it looks like I could say that I at least have it down to accuracy to the nearest hundredth. Because of course all along as we're looking here, we were realizing that our actual area was always going to be bound in between this lower sum and the upper sum. Now, the other thing we want to look at then as we look at kind of making some observations is that no matter which side I was coming from, whether I was coming from a lower sum, kind of a lower estimate, or an upper sum or an overestimate, or maybe I would have been coming from a combination, like not really sure if it's a lower upper, if I would have used midpoints instead of left endpoints or right endpoints, for example. It didn't really matter as long as I was letting the number of rectangles get bigger and bigger and bigger and bigger. In other words, approach infinity. So what we really want to observe here is as the number of rectangles, as n is going to infinity, both the lower and upper sum, so the lowercase s sub n and the capital S sub n, both of these are closing in on the actual area. So whether I used a lower or an upper, left endpoint, right endpoint, midpoint, whatever it is, as long as I'm letting my n go to infinity, then these sums as n goes to infinity would give us the actual area. So this is where our notion of the limit is going to come back in. So the limit was foundational in developing the definition of the derivative, and it's also going to be foundational here in developing what we're going to look at as the actual area, the limit of the Riemann sum. That will give us the actual area. So as you look down below in this boxed result here, so if I'm looking at this area under the curve, a continuous function from A to B, if I now let the limit as n goes to infinity, so this is now letting n go to infinity, and what we see on the right-hand side, well, this was what we always looked at before. This was giving us the sum of the areas of the rectangles. So these were, this is the area of those rectangles that we were just looking at. And incidentally, we'll look at other, it doesn't always have to be rectangles. You can use trapezoids and other things, although we're focusing on just rectangles here. So what we had here, this was our delta x, remember from last time. So this is that common width. So we're assuming the same width of all of our rectangles. And then all of these f of x1, f of x2, f of xn, these represent the sum of all of the heights of your rectangles. So if I take the area, the sum of the areas of all these rectangles, and let that actually go to infinity, then this is going to give us now the actual area. So as soon as you throw on that limit as n goes to infinity, now we're no longer using 8 rectangles. I'm not using 18 rectangles. I'm not using 800 rectangles. I am taking the number of rectangles and going to infinity. So as soon as we take the limit as n goes to infinity, if we can do that, we can determine not just an approximation, but we can determine what the actual area is. And whether or not it's a left endpoint or a right endpoint, that was kind of what we were observing up above. This c sub I can be any point in that interval, so it doesn't matter. We've basically done left and right endpoints so far. So what we're going to do now is we're going to use the limit process to find the area under a curve. So notice here we are finding the area. I'm not approximating anymore. It's going to be actually finding the area. So the first example we're going to look at is going to be one that we could actually verify with geometry if we were so inclined, because it's going to be a line. So the function is y equals 3x plus 4, and we're going to look at that on the closed interval from 0 to 3. All right, so let's start off And let's just begin with our definition, right? So I'm finding the actual area. So here's what we know from our definition. The area is going to equal the limit as n goes to infinity of the sum as I goes from 1 to n of f of c sub I. Okay, well now we can start to get specific. F is really this function y equals 3x plus 4. So we're going to have this function 3, and then c sub I is going to go in for x, and we're going to talk about our representation for c sub I in just a minute. Any point in the interval plus 4, so that's f of c sub I, and then times our delta x. Well, delta x, we of course should remember, is b minus a over n. So b minus a over n. Now remember, in this case, we don't have a specific n because we're going to let n go to infinity. Okay, so what do I really need here to be able to take this a step further? I need to talk about representation at this point for c sub I. So we need to figure out how are we going to come up with representation for some data point that is in this interval. I need representation for c sub I. So kind of off to the side, that's what we're going to have a little conversation about here, is what we are going to use for c sub I. And we're going to do it within the context of this example, but we'll generalize it really for any of our examples that we look at. Okay, so here for this example, we have our function f of x is equal to this line y equals 3x plus 4. So this is not drawn obviously with any precise mathematical accuracy here. So our y-intercept would be right here at 4. All right, so here's our line. So this is our f of x here. All right, and we're looking at this partition is going from 0, and then let's just say this is over to 3. So we're on the interval from 0 to 3. All right, well, when we think about, breaking this up into, some rectangles here, that's kind of what we would think about. And I'll just draw in what we might have going on here. And we want to talk about our two classics that we've used so far is we've looked at representation with the left endpoints, and we've looked at representation using the right endpoints. So we want to kind of think about both of these as being viable options because again, c sub I can be any point in the interval, and just kind of decide which maybe we like the look of better. All right, if I start with left endpoints, that means that in the case of the first c sub 1, because my lower index of the sum up here, it starts at 1. So c sub 1 would have to be this 0 right here, because it would be the left endpoint that we would be using. So c sub 1 would have to be 0. And then c sub 2, so for the second rectangle, so we would have to go in a width of 1 delta x. So remember, as we break this up into our partition, each of these are a width of delta x. And in this case, delta x happens to be 3 over n, but I'm just going to write it as delta x. So we would be in one of those widths. So we would be in 1 delta x. We'd have to go in one width in order to get to the left endpoint here for the second rectangle. And so on. So c sub 3, I would have to go in to be at the left endpoint. I would have to go in 2 widths. So I'd have to go into 2 delta x. So this doesn't seem, too bad, right? So what would it be in general? What would it be for any c sub I that I'm trying to represent? Well, let's make the connection. At 3, I go in 2 widths. At 2, I go in 1 width. So I'm always going in 1 less than that. So it would be I go in I minus 1 of whatever my width is. And that would be okay. We could use that. But let's take a look at what the right endpoints might look like here. So if I was going to use right endpoints for the height, the first endpoint, again, my index starts at 1. So if I start with the first rectangle, if I want to use the right endpoint, so now if I am trying to use the right endpoint, then my first one would be right there. So I'm actually starting in, to use the right endpoint, I'm starting in 1 width. When I was using the left endpoint, I started at 0. Now to use the right endpoint, I start in 1 delta x. And so that's where I start my first right endpoint. Then the second height, it would be right here. So now I would have to go in 2 delta x, so 2 widths, and so on. So now I kind of like the look of this better. For any c sub I go in I delta x. That looks a little better. So in general, we're going to gravitate towards right endpoints. It's not that it would be wrong to use left, and in fact, your homework at times may ask you to think about using the left endpoints, but truthfully, the right endpoints are just a little bit easier in terms of their representation here. So here's what we want to kind of think about. So in general, as we think about this, if I was going to use my left endpoints, so the left endpoints would get represented as c sub I would equal. Now we had the advantage in this one that we were starting at 0. But if we were starting like on the interval from 1 to 3 instead of from 0 to 3, you would have to start in at that leftmost endpoint. For us, it was 0. In general, it could be some other value a. But then you have plus this I minus 1 delta x. So this is your representation for left endpoints in general. Your representation for c sub I, if we're going to use right endpoints, is a little nicer. So here, c sub I, again, you have to start at a. We got lucky here, or the first example is a little nicer. A happened to be 0. But then the nicer part of right endpoints is it's just going to be plus I delta x. So this is our representation for right endpoints, and this is just a little bit easier to work with. And so I would say let's go with what is easier, and that's what I'm going to choose to use. So, you know, in my class, in the ones where they say, hey, try it with left endpoints, and hey, try it with right endpoints, and which did you like easier? You know what? If you can just do it with right endpoints and call it a day, that's fine. You're going to get the same result. Right endpoints are easier. So we've discovered that. Let's now not have to always repeat that idea. So we're going to use our right endpoints here. So that is exactly what we're going to do. So now we're going to go back up here, and this c sub I, we've just decided that we're going to use right endpoints. So the right endpoint is going to be a, which in our case is 0, and then plus I times delta x. And delta x in this case, we've already found that, is the 3 over n. So remember, this right here, this was how we computed our width delta x. All right, so now we're in business. Okay, so let's see what we have here. So let's continue kind of back to the original problem here, limit as n goes to infinity. And now we have our sum as I goes from 1 to n. And now we have in this first term here 3 times I times 3 over n. So we could call that 9 over n times I plus 4. And so that times our delta x, which is the 3 over n. Well, this 3 over n factor, I like to just bring it out in front of the sum because it does not have an index of I in it. And so without an index of I, it really can be treated as a constant. And so it cannot come out in front of the limit, but it can come in front of the sum. We'll get to the limit at the very end. Obviously, 3 over n is going to have an impact on the limit as n goes to infinity. So it can't come all the way out in front, but it can come in front of our sum. All right, now the next thing that we're going to want to think about is going back to how we opened this section, which is properties and then formulas involving some sums. And so one of our properties says that we can take a sum term by term. So if I have the sum of this binomial, then I can say, all right, that's going to equal the sum as I goes from 1 to n of the first term plus the sum as I goes from 1 to n of the second term, which is just 4. And in that first term, we can observe that that 9 over n is, again, not impacted by I. There's no I in it. So this 9 over n is really like a little constant multiple that can come in front of that first sum. So we can think of this as 9 over n times the sum as I goes from 1 to n of I, and then plus the sum as I goes from 1 to n of 4. All right, making progress. Now we have some formulas from the beginning of this section. So the sum as I goes from 1 to n of I, that was n times n plus 1 over 2. And the sum as I goes from 1 to n of a constant, that was that constant times n. So now we can evaluate those sums using our sum formulas. All right, we're getting close. So now what we want to do is, you could definitely do some simplifying. It's kind of up to you in terms of how much simplifying you do. Sometimes people might look at some of, like in this first term, this n over n, and just be like, oh man, I just can't not help myself, but wanting to reduce that, and that would be fine. But you don't need to. One thing though you do need to think about is this 3 over n that's in front. That definitely needs to get into both of these terms. So I'm going to just say, all right, let's just, at minimum, I have to distribute through the 3 over n. So in my first term, I'd have 3 times 9, so I'd have 27 n times the n plus 1, all divided by n times n over 2. In the first term here would be a 2n squared. And then in the second term, I would have 3 times 4 would be 12n over n. Now again, sometimes it's really hard to just not want, it's, I think it's almost hard not to want to reduce an n over n. You wouldn't need to, but it's hard sometimes not to. Now in this second term, in the first term rather, I want you to observe that what you really have is the limit of a rational function, right? It is a polynomial over a polynomial. And so when you have the limit as n goes to infinity of a rational function, we talked about this way back with limits, these limits behave according to the rules of the horizontal asymptotes. So in this situation, because the degree of your numerator is equal to the degree of your denominator, in that situation, your limit becomes the ratio of the lead coefficients. So when the degree of the numerator is equal to the degree of the denominator, then it's the ratio of the lead coefficients. All right, so what do we get? The limit as n goes to infinity of the first term is going to be 27 halves. The limit as n goes to infinity of a constant is just that constant, so 12. Or if it had been n over n, you could think of it the same way, degree of numerator equals degree of denominator. So this is like, what, 13 and a half plus 12. So we end up with 25 and a half, an exact area of 25 and a half square units. So that is how we can compute the area exactly. So one of the things that in this example, we'll kind of just move this, sort of our sidebar there, is this was one that we actually could have confirmed with geometry. So just the last little part of this, if we think back to this graph that we had here, so we had, oops, I really just wanted the regular one. So it was the line y equals 3x plus 4. So we know that this y-intercept was right here at 4. So this was my line y, supposed to be my line equals y, line y equals 3x plus 4. And then we were on the interval from, let's say this is from 0 to 3. And so if I am trying to find, this is the area that I am looking for here, is the area under this curve, right? So here's the area that we've just determined is 25 and a half. So I could have found this because I have a line. I could have divided this into two segments. Oops, I need to go back to my thing. I could have divided this into two portions right here at x equals, or y equals 4. So this lower part, well, this is not drawn to scale, of course, but this is a 4x3 rectangle. So this portion, this would have an area of 12 square units. This value, if I sub into the function, that would be 9 plus 4. So this would be up here at 13. So this area would be 1/2 the base times the height. So half of the, so we would have 1/2. My base is 3. Yeah. Yes, 3, sorry. And then my height in this case, well, the height isn't the entire 13. So the height here would have been 9. It would have been the 13 minus 4. So it would have been 1/2, base is 3, and the height is 9. And so this is where here is the 27 halves portion in square units. So we can see that, of course, is exactly what we would get when we would add these two portions together. We get our 27 halves plus the 12. And so on our first example here, we can see that good old basic geometry allows us to check that out and verify our answer. Next time, I will do an example of a quadratic function. Same process, but with a quadratic.